This time we will discuss moment of inertia. So moment of inertia, what is this? If there is an area, say any arbitrary area, if I take a small element inside this arbitrary area, then my moment of inertia of this entire area will be, say if it is about x-axis, is second moment of the area. So what is second moment? That means if the distance is y, then y times dA, again y times y, that means second times. So second moment of an area is called moment of inertia. So again, what is moment of inertia? Moment of inertia is the second moment of an area with respect to an axis. So that is called moment of inertia. So if I consider about x-axis, my moment of inertia about x-axis will be y square dA. So similarly, if I want to find moment of inertia about y-axis, if this distance is say x, then Iy will be x square dA. So that is called moment of inertia. Now, why do we need moment of inertia? Very simply, to calculate the deflection. Say if I have a beam here, if I apply some load here, what will be the maximum deflection here? To calculate the deflection, we need the moment of inertia. If the moment of inertia is higher, deflection will be lower. Yeah. Also, we need moment of inertia to calculate the capacity of a column, so the buckling capacity. Excuse me. So if there is a column, how much it will buckle, it depends on the moment of inertia. Moment of inertia higher means less buckling. So we will discuss this deflection or buckling in our next class. So today our topic is how to calculate moment of inertia. Okay, so for a rectangular section, if my section say this is my section, this is B, this is A, then the moment of inertia about the centroidal x-axis is B h cube over 12. For this axis, y-axis, my moment of inertia will be h b cube over 12. That means for this axis, this times this cube divided by 12. For this axis, this times this cube over 12 about the centroidal axis. Now we will see now how can we calculate it. We need calculus. Now again, if you do not understand calculus, no problem. This is just to show you. So say there is a rectangular section, say this is B, this is A, this is my centroidal x-axis, y-axis. Say I have a small area here, this portion is dx, here to here dx, and here to here will be h over 2. Now, if I want to find moment of inertia about y-axis, this axis, what we learn is second moment of the area. Second moment of the area. Now, so if we consider only this portion, then what is happening? So x square, what is my dA? What is the area of this? So area of this will be dA will be h over 2 times dx. H over 2 times dx. Okay, so h over 2 times dx. Then h is a constant number, it will not change, so I can take h out. Similarly, I can take 2 out. So x square dx. Now, for integration rule, we know that if there is a power, the power increased by 1, and we divided by that increased power. So h by 2 x cube divided by 2 is divided by 3. So the power will increase by 1 and we will divide it by that increased power. Now what is the limit? Limit means, so we are doing about y-axis. So this is my y-axis. So limit will be here 0 and here. So this will be my limit. So this will be b by 2. So limit will be 0 to b by 2, 0 to b by 2, 0 to b over 2. So here my limit will be 0 to b over 2, because we are considering only the quarter part of this rectangle. So if I simplify here, I will get h by 2, then let us bring the 3 out also. So 3 out, then b by 2 cube minus cube. No, minus b by 2 cube. Okay, so if I do that, this will be 6, this will be b cube, and this will be 8. So a is b cube over 48. So a is b cube over 48. Now we consider only quarter part. If we consider the entire part, then my iy combined, say combined, iy combined will be 4 times a is b cube over 48. That means a is b cube over 12. So hopefully you understood how I calculated the moment of inertia about y-axis. So we found that moment about y-axis is a is b cube over 12. Now if we do the same thing about x-axis, we will find this. So now in future we will not derive it every time. We will just memorize it. We will just memorize this value, and we will use this value for to determine moment of inertia for other section. So something else we need to memorize is that if it is a triangular section, say if it is a triangular section, this is b, this is a, say this is the centroid. So about this axis it will be b a cube over 36. About this axis it will be a is b cube over 36. So we will memorize this, or it is in your book. Just make sure that you, when you need it, you can find it. Similarly for circle, moment of inertia about both axes is same, because it is symmetric. So moment about, say, ix, this is y, this is x, ix or iy, pi r to the power 4 or 4, or pi d to the power 4 divided by 64. You can use the radius or diameter, whatever you use, radius or diameter. If it is radius, pi r to the power 4 over 4. If it is diameter, pi d to the power 4 over 4. Okay, then what is the unit of moment of inertia? So if you take this one, whatever, it is a dimension to the power 3. That means total is to the power 4. So whatever your unit is, say if your unit is in inch, moment of inertia will be inch to the power 4. If your dimension is feet, so moment of inertia will be feet to the power 4. If your dimension is meter, your moment of inertia will be meter to the power 4. So that is the unit of moment of inertia. So that is the basics of moment of inertia. If I go more like next time will come parallel axis theorem. Parallel axis theorem. So parallel axis, that means axis should be parallel. Okay, so if I have a section, say here, rectangular section, if I know my moment of inertia about the centroid, say this is my moment of inertia, say right here c means centroid, this is a central axis, and the area of this is a, and moment of inertia here is about ixc, as obvious. These symbols, you can use your own symbol as long as you know what is this. there is no universal symbol for this moment of inertia of this. I'm just using whatever in our book and whatever FE exam uses. So if I know my moment of inertia about this axis, if I need to know my moment of inertia about another axis here, where these two axes are parallel, so parallel axis, if I need to transfer here to here about, say this axis is x bar, then moment of inertia about ix bar will be whatever I know here. So if it is b, if it is h, I know that it is b h cube by 12 here. Whatever moment of inertia about here, that, so b h cube by 12 plus, okay, so there will be a plus whatever the area, whatever the total area that I am transferring times the distance squared, whatever the distance I am transferring, then whatever whatever my initial moment of inertia about the centroid was, I need to add the area of that portion and the distance square. If I do that, then I will get my moment of inertia about this axis. It is very important because in civil engineering, most of our sections are composite. For composite section, we need to apply this rule. So make sure you know this rule, parallel axis theorem. That is very important part. Other thing, other some miscellaneous parameter. Miscellaneous parameter is, say, polar moment of inertia. What is polar moment of inertia? What is this? We represent by commonly J. Commonly J. What is that? Say for triangular section, if I find moment of inertia about x-axis, if I find moment of inertia about y-axis, polar moment of inertia will be ix plus iy. Sometimes we use bar here. Bar, this bar represent the centroidal axis. So it is better idea to use bar. Now, if you do not use bar, it is a mistake? No, as long as you know it. So polar moment of inertia is summation of ix and iy. Same thing here also, polar moment of inertia. If I use, say, bar here, then ix plus iy. That is polar moment of inertia. Other term need is radius of gyration. Radius of gyration. Radius of gyration, what is this? Say radius of gyration about x-axis here. Radius of gyration about x-axis. Say it is r. What is this? E square root of ix bar divided by area. So radius of gyration about x-axis is moment of inertia about x-axis divided by area. Radius of gyration about y-axis is square root moment of inertia about y-axis divided by area. What is polar moment of polar radius of gyration? We represent by whatever the term. Say you are using ZP. Sometimes we Z square root J divided by area. That is polar radius of gyration. Now these symbols are like, it is not universal, so it might change with books to books. So make sure that you know this. Okay, so these are the most of the parameter we needed. Sometimes we use section modulus. Again, section. Okay, let me check your book. What your book uses for polar radius of gyration? So polar radius of gyration. Is it ZP or are you something else was used? 1 minute. now if I come back, so in your book they used it RZ, RZ, radius for Z. See, radius for X, radius for Y, radius for Z. So your book used RZ. Okay, so I think we covered whatever the basic theory we need to calculate moment of inertia. So again here we will memorize some values for triangle, rectangle, triangle, circular, and some other basic section that is listed in your book. We will use that, and we will use that to calculate the moment of inertia or radius of gyration or polar moment of inertia of a composite section. That is our main target. So we need to use the parallel axis theorem a lot. So make sure you understood that. So in my next video I will show an example. Thank you.